somewhere, but I shall try if I could complete the class up to 2:20. Anyways, okay. So I am sharing the video with you. Let's see, sharing the screen. Just a minute, class. Class, can you see the screen?
Yes, sir.
Yes, sir.
Okay. So, class, before I start, let's have a close look at the statement of the maximum modulus theorem before I start with the second version of maximum modulus theorem. Class, you notice that here we were given the condition 1. Condition 1 means that the function is attaining its bound, number 1, and the bound is this. And moreover, this point A at which the function was attaining its bound, this point A was inside G. Take a note. And then the function was coming out to be constant. Of course, some one of you, maybe Ashish or Mamta or those who interact very often, they may say, sir, if you are saying function is going to attain its bound, then this A should be in G. Then where else this A would be? Am I right? If we are saying the function is attaining its bound, then certainly this A must be in G. Right, class?
Yes, sir.
So, but still, I'm making a special emphasis on it. And I am putting it this way. Function is attaining its bound. And because the point at which the function is attaining its bound is within G, that's why the function is constant. Now you may say, sir, if function is attaining its bound, then certainly it will have to be in G. Why you are saying so? I repeat, it is given to us in this theorem. This is something very important, class. If function, the theorem says that if function attains its bound, and the point at which the function is attaining its bound is inside G, then function must be constant. But if it is not in G, and function attains its bound, then maybe the function, it may so happen that function is not constant. Now, you will be surprised, sir, what all this you are saying. In fact, class, there is something in my mind. And what is that something? That something is this, class. Yeah, now I'm starting. So, class, in maximum modulus theorem, first version, we saw that if the point, which was point A actually, If the point at which, of course, along with the given conditions, we saw that, of course, along with the given conditions, F is analytic on G, and all those things are there along with the given conditions. Certainly, I am not talking in isolation. This is understood. So, in this, we saw that if the point A at which the maximum is attained, the bound is attained, which is maximum certainly, because mod of fz was less than equal to mod of fa for all z's. So certainly I can say it maximum. If it is not attained, and we had the same condition, mod of fz less than equal to mod of fz less than equal to some capital M, then certainly you would say that either upper bound, or you would at the most say that to be the least upper bound. But if it is attained, then certainly it is maximum. Is attained, is within G, then it leads to F being constant. Now the class point is this. We had G. Our function was defined on G. It was analytic and all other things. In fact, the class, there is something which is even beyond G. And that is actually, one thing is boundary of G, and one thing is the limit points of G. Some of the limit points of G may be in G, some may be outside. And class, you know that uh, if you take this G along with the boundary of G, or class, if you take G along with its limit points, in both the situations, what do you get, class? You get G closure, right, class?
Yes, sir.
So what I am trying to say is that suppose that A at which the bound was the function was attaining its bound. Suppose that is not in G. Suppose that is in this, in G dash, or boundary of G. Assuming that boundary of G or G dash, they are not uh, contained in G, because in case they are contained in G, then it will be G again, and we will have the same situation. So maybe we may have a way such that we define F on G closure, and we say that now there are two parts of G closure. One is this, one is this, or if you look at it from this point of view, and then we can say that F is satisfying all those conditions which were there in first version on G, and F satisfies some condition on the remaining part. Let us say G dash. So that is the limits. Then maybe it may so happen that the function may attain its bounds, or G dash, or you can say boundary. Then it may happen that function will not be constant, and it will be attaining its bound at some point in G dash or at the boundary of G. And in that situation, function need not be constant. So actually the first version says that if that very point at which the function attains its bound is within G, then certainly that will force the function to be constant. But if that point is not within G, then it may not force the function to be constant. I mean, it may happen that function may attain its bound without being constant. So that's the idea. And basically that's the idea of the second version of maximum modulus theorem, which says that if this is the situation which I have narrated here, then then maximum modulus theorem second version tells us that function will attain its bound at some boundary point. And in that situation, that will not force the function to be constant. Because classic function becomes constant, then there is nothing much to do with the function. So basically, that's the idea behind the second version of the maximum modulus theorem. So basically, so basically, what we will be doing, we will be making a slight change in the conditions of the theorem, and the second version will give us an idea that without the function being constant, we shall be, I mean, the function shall be obtaining its bound, and that bound will be obtained at the boundary. So now I am starting with the precise statement of the maximum modulus theorem, second version. So, class, let me tell you that actually now I have moved on to chapter 6 all of a sudden. In fact, class, there are two sections in your course from chapter 6. That is the last chapter in your course. And this is the first section of chapter 6. So, looking into the continuity of the concept, I have moved on from chapter 4 to chapter 6. So, so this is basically now I am in section 1 of chapter 6. So, the section 2 is about the Schwarz theorem. So, I will not take up that. After completing this section 1, I will be back to section 4. So because these are interlinked, that's why I'm moving on to this section. So maximum modulus theorem says class that so class C, let G be open and bounded. So class, the first change, if you remember, in maximum modulus theorem, we took G to be connected, but now we are taking G to be bounded. First change. Let f be a function defined from G onto C such that number one, f is analytic on G. If you notice, this condition is same, and it is given to you. Yeah, okay, you can take here bar, and it is given to you that f is continuous on G bar. So the function is analytic on G, and it is continuous on G bar. So okay. Then the maximum modulus theorem second version says that then maximum of this set simply means the maximum of the values of the function. So class, the maximum modulus theorem that says that this maximum will be same as the maximum of the values of fz when z belongs to the boundary of G. Meaning thereby is what class? It means that this number, that is the maximum of the values of fz, will be obtained at some point which is in the boundary. So this I can, in short, this I can write like this. That is maximum is attained only at the boundary of G. Class, you must have read the concept of boundary of a set at the undergraduate level in the metric space theory paper. So I assume that you have basic idea about the concept of boundary. Boundary is simply the collection of all those points whose distance from the set as well as from its complement is zero. I mean the points those points of the set which are at the frontier of the set and its complement. Those are called, the collection of all such points is called boundary of G. And each one of the elements of this set is called simply a boundary point of the set. So now let's look into the proof class. Class given is G is bounded. Class given G is bounded means this implies that G bar is bounded. The logic is very simple, class. Class, if you remember, G is bounded means what, class? G is bounded means you are given that diameter of G is finite, right, class? This is the definition of a bounded set, right, class?
Yes, sir.
Yes, sir.
And class, if you remember, you have done this result at the undergraduate level that the diameter of the closure of a set is same as the diameter of the set. Yes or no?
Yes, sir.
So it means the diameter of G bar is also finite. That's why I have said that G bar is bounded. Please take a note. At the same time, you also did that. You must have done the example that diameter of a set is not same as the diameter of its interior. Please be careful. Right? Okay. Also, class, also, G bar is always closed by definition. Closure of a set is always closed, whether the given set is closed or not. Yes or no, class?
Yes, sir.
So it means it means G closure is closed, G closure is bounded. So we have a closed and bounded set in C. G is in C, right, class? So it means it is compact. Is this okay, class? Is this okay?
Yes, sir.
Yes, sir.
Now,
Yes, sir.
now you are given F is continuous on G bar. Now because F is continuous on G bar, and just now I have shown you that G bar is compact, so combining these two facts, we get that F is bounded on G bar. We get two things, F is bounded and F is uniformly continuous. We don't require that. Is this okay?
Yes, sir.
So if F is bounded on G bar, this means what, class? Therefore, if you consider this set, bounded means what, class? Bounded means mod of Fz is less than equal to sum m for all z in G bar. Bounded means this, class. This m is certainly this m is
Sir.
positive. Bounded means this. So it means, class, this set is, this set is bounded, right, class? It means this set is bounded.
Yes, sir.
I mean, the same thing I have written like this. Is this okay?
Yes, sir.
Yes, sir.
And class, this is bounded. And moreover, take a note, this is a subset of G closure, which is closed. So bounded set means you can talk of its infimum and supremum. So supremum of this set will exist.
Yes, sir.
So supremum of this will exist, and moreover, that will exist in G bar because G bar is closed.
Yes, sir.
right? Okay, good enough. Because supremum, roughly speaking, because the supremum behaves like a limit point, and because g bar is closed, roughly speaking, and because g bar is closed, so you can imagine that it can't go beyond g bar. Is this okay?
Yes, sir.
Okay, good enough. So it means what? If it is attained in G bar, this exists in G bar, exists not, sorry, it is attained, sorry, yeah, this is attained in G bar, sorry. If it is attained in G bar, class, it means what, class? It means that is, there exists some A in G bar, right? Such that supremum of this set is equal to this. Is this okay, class? We are having some point A in G bar at which we get this value. Is this okay?
Yes, sir.
Yes, sir.
So it means the point is that if it is attained,
तो ये
then
आपने सुप्रीमम ऑफ fx लिखा है,
G G or
x रियल होगा.
सॉरी जी, ये पता नहीं कहाँ से आ गया. अब ठीक है? Is this okay? Right?
Yes, sir.
Or you call it now maximum. It is one and the same thing. It is attained. Once it is attained, it is maximum. Is this okay?
Yes, yes.
Is this okay?
Yes, sir.
So, see, now you see that by the definition of maximum, please take a note that maximum of all such numbers will be bigger than every such number. Yes or no? Yeah, if you take maximum
Yes,
of,
sir.
yeah, so you are taking maximum of these numbers. So this maximum will be greater than equal to each one of these numbers. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Right? Yeah. For all z in G bar, for each of these, that is, मैं थोड़ा साफ साफ लिख देता हूँ. That is actually I am saying, that is, this means actually this is less than equal to mod of A for all z in G bar. In fact, we are getting this. Let me call it number 1. Is this okay? Is this okay?
Yes, sir.
Yes, sir.
Good enough. Now, class, I am going to just make one claim. So, claim that A does not belong to G. See, class, let's try to understand this expression. Class, let's try to read this expression. This expression means, class, bound of, I'm sorry, class, we missed something. In fact, class, rather than starting like this, we should start the proof like this. Now, if f is equal to constant on G, then done. Okay, class? Okay, class?
Yes, sir.
Who said yes, sir?
Sir, yes.
हाँ शीश, लेकिन ओके तो नहीं लग रहा मुझे तुम्हारी आवाज से.
हाँ,
क्यों?
थोड़ा सा लगा कि
यस, नहीं तुम्हें तुम्हारी आवाज़ से मुझे पता लग गया, और एक्चुअली में ये ओके है भी नहीं, क्योंकि ये इतनी आसानी से समझ में नहीं आता। तो आई विल एक्सप्लेन दिस। वेरी गुड, मुझे अच्छा लगा। तुमने रेस्पेक्ट पे यस सर तो कहा, लेकिन तुम्हारी आवाज़ से मुझे पता भी लग गया। सो आई एम गोइंग टू एक्सप्लेन साई। देन डन मीन्स व्हाट? क्लास से ऐसे ही नहीं दिखता है। तो अगर एक बार मैंने बता दिया फिर कन्विंस हो जाओगे, ठीक है? ठीक है। सो देयर फोर, then further for our discussion we will assume, therefore let us assume f is non-constant on G. So class, take a note. We are making discussion in this situation now. Is this okay? I will explain you this side. ठीक है? Is this okay, class?
Yes, sir. Yes.
So once I complete the proof, I will explain you this side. Don't worry. So now you can assume that we are taking f to be non-constant on G. Please take a note that f is defined on G closure, right? F is defined on G closure, and our G closure is the G union boundary of G. Then saying that F is constant on G, how it is going to imply that it is done, right? And how saying that F is not constant on G, how it is going to help us. So see. So first of all, let me complete the proof, then I will next. So in our discussion now, at the moment, our F is non-constant on G.
सर
Yes.
सर एक बार जहाँ पे आपने लिखा है ना कि सेट ऑफ ऑल मॉड एफ जेड जेड बिलोंग्स टू जी सबसेट ऑफ जी बार,
G. Yes.
सर मेरे को
Oh,
वो जी
sorry.
बार सबसेट
Uh,
होगा,
huh? Sorry,
जी
sorry.
बार का सबसेट होगा वो।
सॉरी जी, सॉरी। अरे कुछ और कहना, कुछ और चाह रहा था, उसको गलत नोटेशन लिखिए। एक्चुअली दिस विल बी ए सबसेट, दिस इज इन आर, सॉरी। एक्चुअली वो अटेंड इन जी बार कहना चाह रहा था, वो जो नोटेशन लिखा गलती से समझ रहे हो मेरी बात?
जी
अटेंड इन जी बार को ही मैथमेटिकली लिखा था, पर वो तो गलत लिख दिया ना, क्योंकि ये सेट वो नहीं है, समझ रहे हो? ये सेट तो भाई आर में है। सॉरी। थैंक यू,
जी
थैंक यू,
सर।
थैंक यू, थैंक यू।
ओके।
ठीक है। कहना यही वो सिंबल बेसिकली, मैंने जो लैंग्वेज लिखी है इसी के लिए लिखा था, सॉरी। सॉरी, गुड, वेरी गुड, वेरी गुड, वेरी गुड। अब ठीक है, आगे बढ़ो।
ओके सर।
So now we will claim that A is not in G. So our G bar is G union boundary of G. So class, take a note. So class, I was just trying to read this. So it is, let's try to read this, and this is in fact what? Bound of FA attained at A. Correct, class? Let's try to read it. So we have to read it like this. This is, sorry. This is bound of Fz attained at A. Is this okay, class?
Yes, sir.
जी
Right?
सर।
Certainly it is bound and it is at attained at A, because we are taking this at A. This is the value of the function which we are obtaining at A. Now I am going to claim that A is not in G. C class. On the contrary, let A be in G. So class, if on the contrary A is in G, now just recall what I discussed today in the beginning of this class. So if A is in G, it means what? It means,
G is constant.
yes, it means if A is in G, it means our function is attaining the bound, and the point at which it is attaining the bound is in G. And then according to, and therefore by maximum modulus theorem first version, then F will turn out to be constant on G. Yes or no?
Yes, sir.
Yes.
Right? and which is a contradiction because for our discussion A is not constant, right class? Is this okay?
Yes, sir.
So therefore, where will this A be? Certainly you are left with this only because it is not in G, but ultimately A has to be in G closure. You can't go beyond G closure. So this means A belongs to the boundary of G. It means what class? That is the bound is attained. That is the bound is attained at a point of the boundary. Yes or no? Is this okay?
Yes, sir.
Fine, good enough.
Yes.
सर
So
एक बार ये बताइएगा
जी जी
सर वो कॉन्ट्रडिक्शन क्यों आया है?
हाँ कांस्टेंट ऑन जी है और लेकिन आपको ध्यान होगा मैंने अभी जो करेक्शन कराई थी हम अपने डिस्कशन के लिए जी को एफ को जी के ऊपर नॉन कांस्टेंट लेके चल रहे हैं, ठीक है?
जी सर।
बट अच्छा वो तुम्हारे पूछने से ये जो अभी साई रह गया था, साई एक्सप्लेन करना, ये एक्सप्लेन करता हूँ। क्लास देखिए, नाउ आई एम एक्सप्लेनिंग साई।
सर जी कनेक्टेड कैसे होगा?
G is okay. So I think you are asking this question because I have used first version, right?
Yes, sir.
Right. Good question. Just a minute. What are the conditions on G bar? G is analytic on G, open and bounded. Yeah, saying that it is open and bounded is not. Yes, you will have to take the connectedness also, class. At least apparently I don't see that where from I will draw the connectedness. So I am adding connectedness. Thank you. Who pointed it out?
Sir, Suman Mondal.
Yeah, Suman Mandal. Correct. Thank you. Thank you. Because if we want to apply the first version, then we should have the connectedness also. And all of us know that just taking open and bounded certainly will not help us for connectedness. A set which is open and bounded need not be connected. We know this. Right, class? Very simple example. For example, you take in real line, what to talk of complex. You take this set S. This is open, right? This is bounded also, but this is not connected. There is a gap between 1 and 2, correct?
Yes.
Yeah, so thank you. Thank you, Mondal. We will have to take the connectedness also. Thank you. So now I am explaining you this psi. So I said that the psi was if f is constant on G, then done.
So what is the reason in the,
Region means?
if there is something is defined on a region?
Oh, region. Yeah, I have told you. Region means simply open and connected. This is just a single word for open and connected. Right? Region is just a single word for open and connected. Right?
Okay, sir.
Right? Okay. So now I'm going to explain you this. If f is constant on G, then done. How? So see. So if f is constant on G, I'm going to claim that f will be constant on G bar. And once I show you that f will be constant on G bar, it means class what? It means because the f is constant, so at every point it is attaining its bound. Yes or no? Constant function attains its bound at every point, not automatically. Right?
Yes.
In particular at the boundary points, because G bar includes G as well as the boundary. So the discussion will be trivial. So G will attain its bound trivially at the boundary points. In fact, a constant function attains its bound at every point of the domain. Yes or no? Yes or no?
Yes, yes.
Yes, sir.
Yeah, yeah, that is something trivial. So the only thing left for me to show you is that f is constant on g bar as well, so that it is constant at boundary also. So f will be constant on g bar. I am going to show you this. And for this class, what I do, let me take sorry. So let me take z to be some limit point of g. Please class take that g bar is same as g union g dash. So this time I am taking advantage of this frame. So class, let g be in z dash, that is the limit point of g. Then class, you know by definition, then there exists a sequence zn in g such that class, this sequence will converge to z. Yes or no, class? Right, class?
Yes, sir.
And this implies that f of zn will go to f of z. Why, class? Because you are given that f is continuous on g bar. So I have used the continuity of f. Is this okay?
Yes, sir.
Yes, sir.
Or I can write it like this, class. Or fz is equal to the same expression, I can write like this. Is this okay?
Yes, sir.
Okay, sir.
Now see. Now I have said that f is constant on g. I have assumed this, na? That if f is constant on g. So if f is constant on g and these zns are coming from g, it means the value of f at all these zns will be just a constant. Suppose that constant is alpha. Yes or no? Right? And the limiting value is coming out to be alpha. It means what, class? That is fz is also coming out to be the same constant. And please take a note, z was any arbitrary point in g dash. It means, class, that is the function f is constant on the whole of g bar. It is constant, it is having the same value at all the points of g dash as well. And it was already having same value at all the points of g, and therefore f is constant on g bar. Is this okay? Is this okay? And if it is constant on g bar, certainly at all the points of g and at all the points of boundary, it will be attaining its bound automatically, and that bound will be nothing but its value. So this phrase is automatically, this is automatically accomplished. So there is nothing to discuss if f is constant on g. That's why I assumed that let us take f to be non-constant on g to make a meaningful discussion. Is this okay? Is this okay? No.
Yes, sir.
Remark. Class, now I'm going to give you a remark. And the remark says that the condition, this is an important remark, that the, so if you notice,
सर
if you, yes,
सर मतलब हमने तो बोला था कि मैक्सिमम इज अटेंड ओनली एट बाउंड्री ऑफ जी, तो सर
जी,
तो बाउंड्री पे भी आ रहा है, जी में भी आ रहा है
क्या चीज, कहाँ पर?
सर, जो ट्रिवियल वाला केस था।
हाँ हाँ, मैं वही कह रहा हूँ ना, तो इसीलिए तो ट्रिवियल वाले केस के अंदर कुछ डिस्कस करने के लिए है नहीं ना, मतलब अगर f कांस्टेंट हुआ तो यू हैव नथिंग टू डिस्कस। पॉइंट इज दिस, देखिए हमने कहा द इट विल बी ऑब्टेन्ड एट द बाउंड्री, लेकिन जैसे ही हमने उसको कांस्टेंट कहा तो वो बाउंड्री वाली सिचुएशन रही नहीं, वो वर्जन 1 बन गया अपने आप ही ऑटोमेटिकली एक तरीके से, तो इसीलिए उसे वर्जन 2 का पार्ट हम बना ही नहीं रहे हैं उस केस को। बेसिकली दिस इज व्हाट आई एम ट्राइंग टू से।
ओके सर, आई
भाई
गॉट
आप
इट।
खुद ही तो कह रहे हो, आप खुद ही तो कह रहे हो कि सर फिर बाउंड्री पे नहीं, वो तो हर जगह कांस्टेंट हो गया।
जी सर।
तो वर्जन 2 का पार्ट तो तुमने खुद ही उसको एलिमिनेट कर दिया, तो दिस इज एग्जैक्टली व्हाट आई हैव डन।
ओके
ठीक
सर।
है, तो वर्जन वर्जन 2 के अंदर जो है उसको हमने पहले इसीलिए एलिमिनेट कर दिया, ठीक है, ओके, गुड एनफ। सो अब रिमार्क देखिए, अब देखिए क्लास, इस रिजल्ट को करने के लिए हमने क्या किया है, जी के ऊपर एक ही एडिशनल कंडीशन ली है, राइट। Mondal pointed out कि सर connectedness नहीं लिया, sorry, we have added the connectedness, but if you compare it with the previous theorem, besides connected and open, we have taken this condition of boundedness on G, right? And this is very important. So maybe you can discuss about the other conditions also, but so far as your course is concerned, I am supposed to discuss about the boundedness of G, and the remark says that the condition of boundedness on G can't be dropped. So this boundedness condition on G is essential. Actually, it is this boundedness condition on G which forces that this particular point at which the function will attain its bound will be in the boundary. This boundedness condition creates that situation. So I am going to explain you this remark with the help of a counter example, where I will drop the condition of boundedness on G, and we will see that actually instead of attaining the bound, function will not in fact attain the bound at all. So let's take that counter example. So class, let me take this G. So I'm taking this a counter example to explain this. So I must write it like this. For example, let G be this. G is the collection of all those complex numbers such that, and you know that complex numbers are of this type, such that the imaginary part always takes value this. So it means class, you can see that there is no restriction on x. It means x will be taking values anywhere from minus infinity to plus infinity. And if you look at the geometry of G class, so I think this is quite clear that G will be this strip of infinite length class. This is y, this is x, this is origin, and this is pi by 2, and this is minus pi by 2. So there is no restriction on x. So it means I am taking all this whole strip of infinite length. Is this okay, class?
Yes.
Right. So it means this is very clear that G is not bounded, right? Clearly, G is not bounded. There is nothing much to explain in it. This is not bounded, it is just obvious. Now, define this function. This has f of z is equal to exponential of, it means it is what you write as e to the power z, something like this, right? You have this function exponential of exponential z. Okay, now not only this, it's not bounded, and moreover class, if you observe, this is also very easy to observe that this G is open as well as connected, because it is not containing its boundaries. If you see here, I have put dot dots. Here you have strict inequality, right? Right, class? So this is clear that it is open as well as it is connected. Is this okay? The only thing which we have compromised is the boundedness, because only then and then we will have to we will be able to see the impact of the drop of this particular condition. Is this okay, class?
Yes, sir.
Okay, so we have dropped the boundariness only. Now, class, clearly f is, you know that class, this function is composition of two analytic functions though. So trivially this f is analytic on g, is analytic on g. In fact, it is analytic on g bar, because if you, even if you take the limit points, these will be the limit points, boundaries, sorry, because these inner points are also the limit points, boundaries especially. So is analytic on g bar, that is obvious, because you know that exponential of exponential z, that is entire actually. So if you don't want to say analytic on g bar, just to be very specific to your requirement, what we can say is that g is analytic on g and continuous on g bar, so that you don't get confused. You have exactly the same kind of thing, though it is analytic on g bar. Something more you can have, but you need only this much. Now class, what is the boundary of g? Clearly class, you can see that boundary of g is x plus minus pi pi by 2, such that, right, it means the which I have marked with the orange dots, this is the boundary, right class?
Yes, sir.
The distance of or any point on these orange dots from g, this is g, and outside g, that distance will always be 0. So this is g complement, of course. So this is the boundary of g, collection of all boundary points. Now, see, if z belongs to boundary of g class, then let us compute fz. Then class, if you compute fz, then it will be class expo of expo of, and any point on the boundaries of this type. Is okay? Is this okay?
Yes, sir.
Right? And if you compute it, then you can see that, okay, now compute this separately, x plus I pi by 2, this will be equal to e to the power x into e to the power plus minus I pi by 2, and this you will get, if you elaborate it, I hope you can do this, this is very easy, you will get plus minus I e to the power x. Is this okay? Very easy. Is this okay?
Yes, sir.
Therefore,
Yes.
therefore, modulus of fz is equal to modulus of expo, and now you put its value. Its value is this. So this exponential comes here as it is, and you are putting its value. So this is plus minus I e to the power x modulus. And class, you know that this is nothing but something like this only. And you know class, whatever this angle is, e to the power plus minus I theta is always, its modulus is always
1.
1, whatever it is. How does that matter? It means class what? It means class, I have shown you, that is, I have shown you that the modulus of fz turns out to be 1 for all z in the boundary. So it means at every point of the boundary, the value of the function is coming out to be 1. Is this okay? Value of the mod of fz. So now I am going to show you. So if it is so, if the theorem, if had it been so that the theorem was to be obeyed, then certainly class, this would have been the upper bound of the function, because according to the theorem it must be obtained at some point of the boundary, then certainly one should have been the upper bound, yes or no?
Yes, sir.
Yes, sir.
If we assume कि theorem true होती तो, लेकिन theorem true नहीं होगी इस केस में, क्योंकि हम कुछ गड़बड़ कर चुके हैं, और वो गड़बड़ क्या है, ये, ठीक है. So now I am going to show you that. So it means, class, what I am going to show you, I am going to show you that if I take some point in G, then I will be showing you that there are points in G at which you can't control the value of the function, and hence it means theorem fails, because according to the theorem ultimately at the boundary point you should have got the upper bound, right? Is
Yes,
it
sir.
okay? Okay. So, but that's why I'm writing here, but. And in fact, class, let me tell you, there is just not one point. In fact, there are plenty of points in G at which the function will explode. You can't control the function. But for any z of the form this, which is an R plus, and certainly, class, this is contained in G, right? Because G is this strip now of infinite length. So certainly I am taking only this positive part of the real line. So certainly this is a part of G, right, class? Right? And on this part of G, every complex number will look like just x only, because it will be plus 0 I. Imaginary part, there will be no imaginary part, right? Right, class? We have mod of z is equal to, what do we have? This is expo of expo x. That is, class, what you can say, that is something like this, e to the power x. And class, if you notice, in this strip there is no restriction on G. So clearly you can see our x is here. Clearly you can see that as we go on increasing x, this will just explode. As x becomes large, this will explode. This is exponential to the power exponential, class. You know this, that even if you take first you take x is equal to 10, then you take 100, and then you 1000, even then it will explode so fast, because first you will take e to the power 10, and then you will take further e to the power 10. So it will explode very fast. You even don't need to go up to infinity. Even if you take x is equal to 10 to the power, let us say 5, even then it will just explode. I doubt if any computer will be able to calculate it, because then it will be e to the power 10. Am I right? Those who have knowledge about the computer programming, they may tell me whether computer will be able to compute it or not. It will explode, right? That is in fact I have tried to show you that mod of fz can't be less than 1 for all z in G. There are some z's in G. In fact, not some. In fact, there are an uncountable number of z's in G which are creating problem. Hence, the theorem, maximum modulus theorem, second version, fails. Fails. The values of the function at the boundary points, these values are not able to control the function on the whole of G. अगर ये जो है वो अटेनमेंट होती बाउंड की, तो जी के सारे एलिमेंट्स के ऊपर वैल्यू 1 से नीचे नीचे रहनी चाहिए थी, क्यों क्लास?
Yes, sir.
Right? So here I have tried to explain you that the condition of boundedness, that was an additional condition, that is a must to be taken. It is actually that condition which gives us the second version of maximum modulus theorem. Okay, good enough. So, class, I have shown you that we can't drop the condition of boundedness. But let me tell you, so I will be stopping with this note that though we can't drop the condition of boundedness, but class we can replace it. So I am writing just 3 or 4 lines, and after that I will stop. So I'm going to put a remark here. Remark. Though we can't drop the condition of boundedness of G in maximum modulus theorem, second version, but we may replace it. It means with some other condition. And not only this, also it is possible to drop the condition that f be defined and continuous on G bar. Plus, if you recall, we took this additional condition that f was defined and continuous on G bar, right? This was an additional thing as compared to first version. In the first version, we talked of the defining of the function f at the set G only, right?
Yes.
So, class, this replacement of the condition on G, this dropping of the condition of the defining and continuity of f on G bar, these things result into the maximum modulus theorem third version. But class, for this we need some machinery, need some tools. So class, next time, first I will be introducing these tools, and then I will be finishing up with this third version of maximum modulus theorem. So let me stop over here now. And with that, class, the first section of chapter 6 will be over. And then I will be back to chapter 6. So anyway, class, today I have just touched the boundary of your course, because your course is only up to section 2 of chapter 6. So just give me 1 minute. Okay, class. Thank you very much. I have taken your attendance. So on Monday, on Tuesday, now first I will be introducing some 2 or 3 definitions, and then I will take up this third and last version of maximum modulus theorem. Thank you, class.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you.